Yeah, hi everyone. This is going to be the talk, Modern Functional Cryptography. My name is Jose, and I'm going to talk only maybe 1 minute about myself. I'm a software engineer at a small German startup called Amy GmbH. It has absolutely nothing to do with cryptography, so I'm going to keep going. I'm an open source contributor to like a bunch of the FP ecosystem in Scala. So HTTP4S, FS2, Scala Z. Then I'm also an author of a security library called TSEC, which is a work in progress. Part of the reason it's not heavily advertised is because I get to play around with a lot of the abstractions that I do, and a lot of them we will see in this talk/workshop. And then the final thing is that I'm an honors computer security student at York University. And then just some thank you to some of the people that helped me out cryptographically. Oh, hi. Just some thank you to Patrick Ingram, Mohammed Reza Fagani, Navid Mohaged, John DeGoes, and everyone in LambdaConf, like all the staff, for making it happen. And then some of my OSS friends. So anyway, just a quick disclaimer about this talk. This is a foundations workshop, but it's not. Hey, Christopher. It's not like a purely beginner workshop. So this workshop kind of assumes a little bit of knowledge of the Scala language, although I will try to be a little bit agnostic about it. But I'm going to be covering topics with respect to cryptography from the ground up. So when it comes to a cryptographic subject, I'm going to be talking about it as if like you guys have never seen it. But the reality is that the majority of you will have touched cryptography at some point. Sorry? Where's Dana Scott?
I thought he was 204.
I thought he was 204. Thank you. All right, anyway, I'm going to continue. I'm going to be covering topics here kind of like as if you guys never have seen cryptography, which is, to be honest, not true. Anybody that works in software development does touch cryptography. So it's part of the reason is because I'm going to be covering certain topics formally. So I'm going to be covering them from the ground up. And that's kind of why I'm going to go from the very, very, very bottom. But that gives me some flexibility in that we have a lot of topics. And if you guys feel not very comfortable with a particular topic, you can slow me down. I think I'm more concerned with people getting something good out of this talk than I am about covering everything. Because ultimately, this talk is not going to teach you cryptography out of just in 6 hours, right? As an example, a college course will take something like, for like 3 hours a week for 12 weeks, 36 hours. I have 6, so I have to sacrifice something. I have to sacrifice most likely depth. So with that in mind, that's kind of, I'm trying to set the tone for how the talk is going to go. Wow, more people than I expected. It's okay. So anyway, so you might be wondering, or might not, because I mean you're here, but you might be wondering why you want to learn it in depth. And you might be thinking like, I'm just a software engineer. I'm not going to be a cryptographer. Why do I need to learn it mathematically at all? Or when am I ever going to touch cryptography on a primitive level? And I'm going to actually, before I even get started with the first topic, we're going to go through like 2 vulnerabilities that happened, one of them recently, and they're not exactly related to the pure implementation. So the first example I'm going to give is the padding oracle attacks and Poodle. This attack was on a CBC mode of encryption, which we will talk about later. And padding oracle attacks really were more because of implementation. So it's kind of padding oracle has to do with how you terminate a ciphertext and how you check the end whether it's in a correct format or not. We'll be talking about CBC mode encryption, so don't worry too much about the implementation at all for now. But it's mostly concerned about how it's terminated, like this attack. And essentially, software developers thought, because I'm adhering to this standard, this ciphertext should be terminated in this way. If it's not, let's throw an error. And it turns out that that ended up like raising a vulnerability where people or attackers could keep prodding for a particular ciphertext, and they could change bytes until one of the bytes matched, right? Because if it did match, it wouldn't throw an exception. Otherwise, it would. And that is why it's called an oracle, in that it's kind of like asking the server, hey, like, let me go through all these really like on purpose wrong ciphertexts until you give me a right answer. And that's what padding oracle was about. And this, like the latest version of padding oracle was in 2016, something called the Lucky 13 attack. It was a variant of it. But then the most notable one was in Poodle, which is padding oracle on downgraded, it's on downgraded TLS or SSL. So basically, you know, SSL has something called like the algorithm negotiation. There was essentially a vulnerability where, for legacy compat reasons, which is again not related to cryptography directly, but to software development and lack of understanding, that they allowed you to use a less secure protocol, and then they ran this attack.
Question?
Sure.
How many bits is the cipher?
We'll get there. Don't worry. I'm only covering why, like, you know, not understanding this can be an issue.
Yeah.
I'm not touching ciphers yet. Yeah. Well, that's literally the first topic. The next example of a real-world attack is eFail, which happened literally as I was making this talk, which is, you know, only basically a few days ago. And it's essentially a vulnerability in OpenPGP and SMIME on essentially standards-compliant clients. And there's two parts of it, but I'm not talking about the first part because the first part has nothing to do with cryptography specifically. I'm talking about the second part. And again, ignore this part. We can return to this slide later because I'll be explaining this. But in general, because of lack of understanding of CBC mode encryption, right, attackers managed to inject tags, right? So even before I explain ciphers, this is, for example, a normal one. And if you guys have obviously done HTTP, most likely, you know that headers such as content type exist when you're trying to send like a message to another client. Like I have multi-part form data, I have JSON. Then because of knowing that this header was always there on essentially on standards compliant clients, then attackers could essentially forge a particular message, here a particular tag, HTML tag, to take everything up until the end, and then it would essentially like move all this data up until the end to whatever this, for example, let's say efail.de, send all of that like decrypted information. So essentially, it's a man-in-the-middle attack. So this was on an intercepted mail, and this could, you know, you would think you're using OpenPGP for encrypting your emails, but it happens that, you know, due to this like misunderstanding, that your email is not actually encrypted and all of the information is public. And this is not exactly an issue with a primitive. It's an issue with like misunderstanding about how you can attack certain primitives. So that's why I think it's important to understand them in depth. And I'm gonna finish around the disclaimers and before I start. You know, these again, this I just talked. This is mostly an issue with understanding, and then we just have to be mindful as developers what we, you know, implement with cryptography. And by the way, I talk really fast, so just feel free to tell me to go slower. But yeah, so as a last, you know, little disclaimer, I just want to say don't roll your own crypto, even though we will be rolling a little bit of our own crypto here, but don't actually do it. Let the cryptographers that know what they're doing do it, and never roll your own custom cryptography. For every single primitive, it takes like 10 years of a bunch of guys, like, and girls obviously, analyzing a primitive and looking for vulnerabilities, and it takes years to find a suitable cipher or hashing function or whatever. So, you know, you're never going to be smarter than an attacker. And I really hope that the talk doesn't end up like this. Sorry?
Oh, just as an example, I think Ketchik took 10 years to get accepted.
Yeah, exactly. And right now, the Caesar cipher, the Caesar competition, which is the one for symmetric ciphers, has been going on, I think, almost 10 years now. I think it's going to be 10 years maybe next year or this year. I'm not sure. I don't remember. But I'm hoping that because this talk is a mix, it's a mix of mathematics and software implementation, that I hope that it doesn't end up like that. That, you know, I kind of speak some math and then, whoa, suddenly I have bunch of cryptographic stuff. So I'm hoping it's not like that. That's what I'll be trying to avoid. And then part of why it's called modern functional cryptography is because I'll be talking about not necessarily laws, because certain cryptographic primitives, not all of them, have a little bit of a weaker notion of a law, not necessarily laws. So some of them are more like properties that are verified mathematically, but they're not exactly laws, and some of them are. So we will be talking about it from an API design perspective, about how we would make an API in terms of algebras. But I do want to make it clear that not everything is necessarily a law. And then this is just some resources. I'm not going to talk about them right now. This is for when I publish the slides. Then if you guys want to continue reading, and if you guys happen to like this talk, then these books are incredible. They're all good. And I probably basically stole my talk from these. So yeah, so these books are just really, really good. 99% of my figures I got from there. And a lot of them go a lot further in depth than I ever will. And it's okay, like I will be publishing these slides, so you don't have to, worry about taking them now, like a picture. Anyway, cryptography is kind of in a really interesting place, and kind of why I like it. It's a mix of a bunch of different mathematical disciplines. It's not just one. It's number theory, abstract algebra, combinatorics, mathematical logic, and information theory. And there's more. If you go into lattice-based crypto, which I'm 100% sure we're not going to have time for, then you will see algebraic topology. And you're going to see problems around algebraic topology. But in general, it's kind of this nice conglomerate of stuff. But that's what makes it so cool and so interesting, that you'll find some things come naturally from so many different fields, and it ends up working out into this really interesting thing that makes your life run, because everything that you're using now has some cryptography now. SSL, all your browsers, your passwords, everything touches cryptography now, except stuff that's not digital. But so these are the topics that we're going to be covering in that order. So we're going to start now with ciphers and computational security and modes of operation. Then we're going to go through cryptographic hash functions, then message authentication. Then we're going to go, after message authentication, we're going to split, and we're going to go into public key and asymmetric cryptography, which is going to be, the first part is going to be pretty much purely math. So introduction to number theory, modular arithmetic, and abstract algebra, and that's going to be lightning fast. So if you are not comfortable with those topics, please do speak up, because these are lightning, it's like one slide for explaining groups and rings and fields. So yeah, slow me down. And then we're going to go talk about the discrete logarithm problem. Yes?
I was just wondering, if you're comfortable with this, just an idea is that there's probably some knowledge bases mixed in this room, so you could break into teams, the less mathy people and the more mathy people could.
I would like them to intermingle, actually.
Sure.
Because I would prefer more generalized progress of everyone else, because in general it's not I'll say again, I'm not teaching you cryptography in this one leap. I only have 6 hours. I want to essentially inspire you to learn more cryptography, and essentially, if you happen to I want to implement user authentication, then you have some tools to do it. You're still gonna have to Google around, but I want to show how fun it is, and why it makes me excited, and why it makes me talk really fast. But all right, so let's start with symmetric cryptography. Now we're gonna start with a historical one. And that's way back in the time of Julius Caesar. They were kind of interested in passing these little notes around in their Senate. And back then there was obviously no notion of cryptography. So what they were wanting to do was pass little notes and communicate in secret. And back then their scheme was actually super, super simple. It's called the Caesar cipher. How many of you have heard of that? Probably okay, most of you. So I'm not going to go into it then, because you guys already know what a Caesar cipher is. Then, after the Caesar cipher, I guess the next thing people tried is a monoalphabetic substitution cipher. Have you guys heard of that one? Okay, so only one person. So I will talk about a monoalphabetic substitution cipher, because you guys know Caesar. Monoalphabetic just means under the same alphabet. So, if we have our alphabet, let's call it A. We have A to Z, right? Monoalphabetic is just the simplest notion of replacing one letter in a fixed way with any other letter. So this could be J, this could be K, this could be K. There's not necessarily a rule. It could be just a lookup table. So monoalphabetic substitution ciphers is, I guess, what some random guy thought would be, this is pretty interesting. I can hide my things a little bit better than Caesar cipher can, because Caesar cipher has a fixed key, and I only have to try 25 letters to see how, or 25 numbers to see how it works. So monoalphabetic substitution cipher took that a little bit further, and it's like now I'm swapping letters out randomly. I should be secure, right? Turns out it's not, obviously. I mean, that's why the rest of the talk is there. But it turns out that when you're speaking, let's say, English, or when you're writing it, you have letters that are more commonly used than others. So the letter E is the most used letter in the English language. And then, I think it's like T, S, and so on and so forth. When you use monoalphabetic substitution, frequencies don't change. So if I were to say, hello world, and I were to map that to some frequency distribution of some letter like A, B, this is like Z is really small. This doesn't change for any non-trivial message like hello world. So you're actually going to see a very similar distribution to how the regular language is going to be like. So for monoalphabetic substitution ciphers, they really are super easy to crack if you just make a histogram. So we need stronger notions of security. But these were the classical schemes. There's more like the Visionaire cipher, but I'm not going to go into those because they're just scribbling on the whiteboard and telling you why they suck. But essentially, what ciphers and symmetric ciphers are trying to accomplish is that if I'm talking to you and I don't want him to listen, obviously I want to kind of put my little message inside a locked box, which I gave you the key beforehand. And I lock my message, I give it to you. Even if he grabs the box, he cannot unlock it. That's what the goal is. So now we're going to get in mathy. In one more. Oh, actually, this is what I just said. So this is the actual scheme. So you take some messages with some key. Both people have the key. And this guy in the middle has no idea. So that's the goal. So now we're going to get mathy with a bunch of mathy symbols, but they're not going to be very difficult to understand. Formally, a private encryption scheme is, you can think of it as a 3-tuple, which is essentially a key generation algorithm called gen, an encryption algorithm called enc, and a procedure for decryption, which is called dec. And then gen is a probabilistic algorithm that is going to choose a key according to some distribution. We'll talk about which distributions are good later. And then essentially the encryption algorithm takes that input, your message plus some key, and it scrambles it. In mathematical notation, for a particular key already set, we call it ENC sub k. And same thing with decryption. And I think I did write the laws. Yep. So essentially it is going to satisfy. Oh, sorry. Go ahead.
Fast.
Yeah. Okay. So what part would you? This is just notation. Don't worry too much about it.
Right. I'm just trying to digest, which things are which types of functions.
Yeah. So you know what? ENC is your scrambler, and DEC is your descrambler.
Right.
Right. One of them is trying to make your message illegible. This one's trying to make your message readable again. And it's going to follow this law. And this is the simplest law. If you apply encryption and decryption on the same message, you have to get back the same message. And this one is actually, you can actually think about this one as a law. Because if this doesn't hold, then you don't have an encryption algorithm. So, yeah, you do. So
What gen does, gen generates entropy.
So yeah, so gen, well, it's not going to generate entropy. It's going to use entropy to generate a key. But gen is mostly to get your key. It's not used directly in the encryption and decryption. But we have to note gen because we have to get keys somehow, right? We have to be able to get a key in some way. Like it can't be just on off the top of your head. But then, sorry?
You mentioned the 3-tuple, the gen, encryption, decryption.
Yeah.
But you also mentioned the message space. Is the message space not included in the description of an encryption scheme?
No, it's part of a property, but it's not part of the 3-tuple that describes the scheme.
Well,
it's
in math, you would say M is the domain of.
I'll get there eventually. I do get to the message space later. Don't worry, it's okay. It's okay. So yeah, I mean, I can make little mistakes like that. It's totally fine to interrupt me that way. So yeah, I was actually just gonna get to message space and key space, which is usually just denoted by K, like this nice font K, and then message space notated by M. And then usually what you want to hold for encryption algorithms and decryption algorithm is the keys in Kirchhoff principle, which is essentially that your algorithm should be secure even if the attacker knows what algorithm you're using, including block size, including key length. All this should be known, and you should still be secure. So now we're going to talk about something called perfect secrecy, which is what we would ideally want, which is, of course, an adversary that knows the probability distribution over your message space, M, which, yes, you brought up. And they know how likely a particular message is supposed to, appear. So it happens that even if they know this, a perfectly secret scheme would mean that the probability of, if you have a ciphertext, right, having a message given that you already have a ciphertext has the same probability of it just being that message. That's all it is. So it just means that if you have a ciphertext, there's no correlation to what message you have. That's perfect secrecy. That means you can't tell at all what the message is going to be. Like statistically, there's not going to be any sort of indication.
Like the ciphertext doesn't introduce any additional information.
Exactly.
About the probability.
Exactly. Exactly. That's
The ciphertext is
C. Ciphertext C.
right.
So yeah, for every message in the message space and ciphertext in the ciphertext space, for which the probability of some ciphertext is greater than 0. So
I can get C. Is C something that's the output of?
yes.
the
So if you run the encryption function
Oh,
and you
N.
get a ciphertext, so I run the encryption function.
C.
Sorry?
Enc of N.
Yes,
C.
exactly.
Okay, yeah.
Okay. So we actually have a perfectly secret scheme, which is called the one-time pad, and it's super simple. You take and usually for the one-time pad, we consider binary strings. That's why this little notation of the brackets of 0, 1 len. So basically all binary strings of length len. So simply for a one-time pad, you take a key picked out of a uniform distribution. So you could get any key at equal probability, and then the encryption algorithm is going to be the simplest thing. You're going to take your message, and you're just going to XOR it with your key. And decryption is and that gives you your ciphertext. So C gives you this. And then decrypting is just XORing the ciphertext with the key. Who is very, cold on XORs and bit manipulation? You all good? Okay, cool. So, we got it. Like, we're done, right? We have a perfectly secure scheme. Why are we not, finished? Probably you already know that one-time pads require the key to be as long as your message. So, if you're sending, imagine if we had TLS over one-time pads, then if you downloaded a 2 GB file, the network connection would be 4 GB because you would need the key to be as long as the message. And it actually happens that you can make a proof that all perfectly secret encryption schemes have to have this property where the key is greater than or equal than the message space. I'm not going to talk about that proof because it's not going to add. It's going to add anything. It's going to add something if you're pursuing this mathematically, but not right now. We're pseudo mathematical right now. We're like almost there, but not quite there yet. Because essentially the proof involves a bunch of manipulating probabilities. So I don't want to get into that for anybody that's very rusty on probability theory. So it happens that we actually want a weaker notion of security than perfect secrecy. We want computational security, which is essentially that we're okay with leaking some information to one attacker that has essentially a bounded amount of computational power, right? So that means they have a bunch of computers with a bounded power. They don't have infinite computers competing and trying to crack your cipher. They have a bounded number, and it's okay if you leak a small amount, right? But essentially, it should be a small enough amount to where it's negligible. For example, if you have a chance of 1/280 of cracking it in every single time, then it's gonna be a lot of attempts it's going to be years, like more years than any of us are going to be alive before you even crack that encryption scheme. And then we can always add more computational power later. So in general, we do want to consider ciphers and make them flexible for higher, I guess, power or like essentially stronger encryption. So we don't want to only consider the resources that we have now. We want to make them like future-proof if we can.
We're still using a Turing computation for most of these, right?
Yeah. So in general, we also don't want to only talk about single message, single ciphertext thing. We also need to have our ciphertext scheme secure against multiple messages. So now I'm skipping ahead because usually like mathematical texts on this go more in depth on what you consider, like how you consider attacks, how you consider something called like adversaries and probabilistic polynomial time functions. Does anybody want me to talk about that, or can I just skip ahead? I think I'm good. Okay. So now we're going to talk about how we actually construct a computational secure cipher. And we want to establish the notion of essentially three things: a pseudorandom generator, a pseudorandom function, and a pseudorandom permutation. And a pseudorandom generator is, as it says, you take some seed or a key. It's simply, this function f, which takes some binary string, which can be your key or your seed, however you want to call it, and it produces another binary string. And it can be an infinite key stream, or it can be a single one. We're not like pseudorandom generators are very abstract. In general, in practice, they tend to be like, for example, really, really long key streams. And then, so that's the first construction. So we want to have something that can generate something pseudorandom for us. And then we want a little bit of a better notion. What if instead of just strings, what if like we were essentially being pseudorandom over the function space? So we don't have one essentially function that has the same distribution for a particular seed. We vary that. It's imagine like if we give it a particular key, right? Then we get a different function. It kind of like imagine like a little lookup table, where if we give it a particular key, we get a function with a different distribution. So that's kind of the concept of what a pseudorandom function is. And a pseudorandom permutation is essentially a pseudorandom function that essentially we're now dealing with permutation spaces. So how many different permutations of like essentially the message space to the key space can we have? And actually a pseudorandom permutation is a pseudorandom function. So one builds upon the other. But in general, our real world cipher schemes, we actually use pseudorandom permutations. So AES does, and et cetera, et cetera. So, all right, let's start with a simple one, like a simple pseudorandom generator, as I just spoke there. So we give it a key, and then we have, so that key, and putting that key into our pseudorandom generator, that gives us a pad of a length that you want. And what if we just XOR that with the plaintext? That is the simplest definition of a stream cipher that I can give you. A stream cipher, the reason it's called a stream cipher is that it essentially generates kind of like a cipher stream that you XOR with the plaintext. That is your encryption. So we want the output of that stream cipher to be pseudorandom, of course. We want it to have this property that it's very hard to crack. But it's a simple, really, really simple concept. But it just so happens that it's not very secure over multiple messages if you just define it like that. Because if you give it, sorry?
Can we go over this more in depth? So
sure.
You have the key before the pseudorandom generator. I thought the pseudorandom generator generated the key, like in the diagram.
We have two generators.
Two generators.
Yes. We can have one that generates a key, and then one that's the actual pseudorandom generator for this one.
Oh.
Yeah.
Okay.
You need to generate the key somehow, right?
Yeah. But
Oh, hello, John.
that process isn't pseudorandom.
Sorry?
Like when you generate the key in the first place, that's not pseudorandom.
That is pseudorandom as well.
So why do we need a second? I mean, I guess it's nice if the second pseudorandom.
I mean, because you're not just XORing the key one time, right? You need to be able to reuse that key. So you want to be able to choose an arbitrary key and then go about your encryption. And then you need that encryption itself to generate a pseudorandom output, so it scrambles your plaintext in such a way that it's hard to find out what is actually happening about it.
It's essentially just the seed.
Yeah.
Pseudorandom.
Exactly. You can think about the key as the seed. Like key or seed in the context of pseudorandom generators are essentially interchangeable.
Okay.
Good to hear?
Yeah, we usually usually happens is you take entropy to some finite set of entropy to generate your key.
Yeah. You're thinking about, like, for example, secure random and using dev-urandom. Yeah.
And then the key is used to then with a pseudorandom function to generate a
Yeah. I'm aware.
infinite-ish.
I'm trying to be more abstract than that. That's kind of why. But yes, you are talking about dev-urandom or how Java's secure random actually works.
Do you have the previous slide for 1 second?
Sorry, the previous slide? Sure. Okay, sure, no problem. Okay, so anyway, obviously these things are not secure over multiple messages, because if you were to give it the same key, you don't have any notion of randomness. And actually, I'm not going to go too in depth about it, but this is actually how WEP was attacked, because certain modes of operation of stream ciphers, which I'll get to in a different slide, require synchronization, and essentially you will have the same output for the same key. So you can actually recover some ciphertext that way. Because of course, imagine if you encrypt the same plaintext. So you use, so let's write up a little bit down on the board with respect to this, because it seems like you guys like this topic. So let's have our encryption function, ENC, take some key k. By the way, there's more than one notation. So it can be ENC some k, or it can be ENC take some k. But let's say it just takes the key and some message m, which is your plaintext, right? If you run this over the same plaintext twice, you're gonna get the same output, correct? There's nothing random. I mean, if you're running on the same plaintext and the same key, I mean, of course. But it should be pseudo-random, but it needs to be deterministic. If it's not deterministic, then obviously you can't decrypt it. Because if you run the key through again, you're not gonna get the same key stream, right? So you need it to be deterministic. You need to be able to decrypt. But this is not multiple message encryption secure, because we're not defining any sort of randomness here. So if I run this same message twice, or even a part of it, I can already decrypt a different message. If I start 2 messages with hello, I already know that they both start with hello, because I can just XOR them together, because they have essentially the same bit sequence. So yeah, I mean, if they have hello at the same bit positions, of course, but yeah.
Can you show that three-way XOR?
The three-way XOR? Sure. Yeah, I can. Sure. So okay, let's give a really concrete example. Let's say we have hello, right? And I'm literally just gonna make up some random bits: 0, 1, 0, 0, 1, 1, 0, 1. This is what hello gives me after running it through some key. We're gonna have some abstract key, right? I'm really bad at these little random ad hoc diagrams, so bear with me. There's some encryption function. I'm making it really tight there. But anyway, we get this little random bit stream, like key stream or bytes from running that, right? And this message says hello world, right? And now I'm the attacker, so I want to know what this message said. So I want to just, so it happens that starting a message with hello is a pretty common thing, right? And so I, as the attacker, can say, hello dash John, right? And then let's say hello maps to 5 bits, and for some reason world maps to less, but that's a detail. I am going to get the same bits, 0, 1, 0, 0, 1, and then this is going to be some other random bits. If I XOR this chunk with this chunk, it's going to zero out. So you have the answer, correct? So that gives you essentially what is called a known, essentially plaintext attack. You already know the result of this plaintext. You have the ciphertext, and with that you can actually extract information about other ciphertexts. So that's what a known plaintext attack is, and this is why this is not multiple message encryption secure. Stream ciphers in general can be, but I'm saying this specific construction of simply a seed and then XORing is not multiple message encryption secure.
What exactly is the information that you can get then? You know hello, something.
You know that the other person wrote hello.
Outputs, and then what are you inferring about what the intermediate?
You know the other person wrote hello because you XOR them, yes. Right? So when you XOR these two, when you XOR an identical sequence, you just get 0, correct?
Yeah, no. Sorry, I thought you were going with this, that knowing that multiple things begin with hello, you can use that to figure out John or world or other parts of the cipher.
No, this isn't. You can, yeah, exactly.
Which means that if a message didn't start with hello, you could get that initial 5 letters of arbitrary message.
Exactly.
Yeah, so that second piece is what I don't understand. How
Yeah.
you get that second piece.
Like the arbitrary parts. I mean,
Yeah.
I mean,
Complicated to drive or-
I mean, under this threat model, you're mostly just extracting part of it. I'm not getting into extracting more of it. It could be that, for example, knowing that hello gives you a particular sequence really reveals some information about the key. In this scenario, we're not considering that, but that can actually happen. Yes?
So your definition of secure is if you obtain any information about the encryption scheme at all, not necessarily the entire message. But
Yeah, exactly.
So we know what messages have and what don't. They have some information, which means
Yeah.
secure by definition.
Yeah, because for example, if you can run arbitrary texts, and we're talking about, let's say, an email or a message, and you're gonna, if you're an attacker and you can run this arbitrarily any number of times, you can just keep trying words, right? If I know it's hello and that's a word, I know there's gonna be a space after it, right? Most likely, it's not gonna be hello dash world most of the time. It's gonna be hello space, and then if I know who I'm targeting, I can extract the name. I can keep trying different words under this model. This is like a super simple attack, but my point is that you are able to extract some information. So at that point, it's not secure. It's not a secure scheme. So we do need a stronger notion of security in regards to that. So we essentially now turn to block ciphers, which are ciphers that essentially work on fixed length blocks, right? So the key stream can be infinite, or it can be just the length of your message. Block ciphers work on fixed length blocks, so you actually sometimes have to adapt your plaintext to match the block length or a multiple of the block length. And we use something called a nonce, or in general, actually, in symmetric encryption, we call that an initialization vector, mostly because it happens to be multiple bits. So it's a one-dimensional vector. Yes?
You're not saying that all stream ciphers will be vulnerable to...
No. I'm talking about this only specific construction, no IV, nothing else. The super bare stream cipher, not stream ciphers in general. I want to make that super clear. So we essentially need to add some randomness to each stream cipher, actually. And that is actually how we make some stream ciphers secure, adding some nonce, some number used once. It doesn't have to be secret at all, because it can happen that for a particular message, you as an attacker don't have control. Most of the time, you're not going to have control over which nonce is used. And nonce means number used once. So most of the time they're randomly generated, or depending on the construction, there might just be a counter that increments, and that's actually totally fine depending on what it is. So stream ciphers, you can add some randomness and then they're good to go. Block ciphers, you need a way to handle arbitrary length messages. And so we're going to talk about modes of operation. Yes?
Point of clarification, the IV doesn't need to be random, it just needs to be varied, correct?
Depending on the scheme, it may have to be random or it may have to be varied. In general, I think you could say varied works, but it depends on the scheme. Like some schemes are actually worse off when they're random. So yeah.
If you could just take like 10 seconds, like
Sure.
what's a stream, what's a block?
A stream is, I'm not even going to talk about keys now. I'm going to make it as dead simple as I can. I have this little ball of stuff, and it just gives me random bits. 1, 0, 1, 0. Okay. This little blobby thing, you're going to XOR with your message. But this is going to be deterministic. Now let's add in back keys. If you have a key, this is going to be the same for your particular key, right? And if you add some randomness, if you add the same nonce again, if you add it, then you're going to get the same stream again. It needs to be somewhat deterministic. We want to add some randomness to protect ourselves. But it's a simple concept in that your message, of course, has a binary encoding. Everything has a binary encoding, or else none of our communications would work. So your message is also a bunch of random bits. Then we take that and we just simply apply an XOR function. And then you know how XOR works. 0, 0, 0, 0, 1, 0, 0, 1. No, this one corresponds to this one. So this is 0, 1. And then it with that XOR, then you manipulate it, and there's your ciphertext. And if this has enough, it looks pseudo-random, and if it is pseudo-random, then an attacker has a really, really hard time figuring out what you actually put in it. That's the thing.
So a stream is just XORing the original message to like the output of your generated stream.
Yes, that's exactly what a stream cipher is. Yes. And for stream ciphers, we essentially have two modes. One is synchronized mode, which is you don't use an initialization vector. And so you simply do this thing where you start it with a key, right? But then remember that I spoke that these could be infinite. These key streams could be infinite. So if you start with this key, you can encrypt the message, and then the next bits that are going to follow are going to be random, right? So why is it synchronized mode? Because if I'm talking to you and I'm using this sort of scheme, we can only initialize our cipher one time, right? And now we have a little blobby number 2. And this is, let's call this little star, because I'm too lazy to write it twice. But this generates star as well, right? And it's just XOR. So remember, when we XOR this with itself again, we're going to get back the original message, correct? So under a synchronized mode, which by the way, I'm not recommending you use because there's been vulnerabilities because of synchronized mode, then, you know, encryption and decryption is essentially based off of state, which is, I mean, theoretically it could be good. But the problem is there's already been vulnerabilities in, what's it called, WEP, which used RC4 specifically. And you could, I mean, the cipher itself was very insecure, but also the fact that it was stateful and you could figure out things about the sequences of the messages, then that ended up being pretty bad. Because I'm not going to get into it too much, but what happened is that they're non-spaced. The range of numbers that were random was actually not very random. So if you guys have ever heard of the birthday paradox, which is not really a paradox, but the birthday attack, then it happened that every so often they repeated nonces, and because of that, you could leak information. So
So just 2 questions.
Sure.
The difference between synchronized mode and unsynchronized mode is synchronized mode we just do the original message. Unsynchronized you have.
I'm talking about the unsynchronized mode now.
Okay.
So yeah, I'm getting that. So that's the part where we add the randomness
Okay.
at the beginning.
And then the second question is,
padding.
can I just do like a quick recap to make sure I'm following?
Sure.
Initially, we do like the one pad thing, which was just general security, and that was an impractical definition of security.
Yeah, because
We added
yeah.
the whole like computational security. But that was a problem because then you can get information across different messages with the same thing. So you can like figure out, oh, hello isn't always messages, so it wasn't secure against multiple message attacks. So now we're doing computational security plus the synchronized mode, and we're basically just getting better definitions of security. That's
Exactly. So essentially what we're doing, and that's exactly the whole theme of this talk. I'm working from the ground up. I'm working about like how did people think about this back then? You know, because RC4 happened, right? I mean, WEP back 15 years ago, that was our Wi-Fi, right? Until people cracked it and figured out it sucked, but because RC4 sucked. But that's how people thought about it. And essentially, somebody came up with synchronized mode because of this. So that's exactly how I'm approaching this talk. I'm approaching it from the ground up. I'm trying to give you the sort of like thought process like some of these people had when they were creating these sort of modes. And yeah, anyway, on synchronized mode, I don't have to go too much into it. Essentially, just add some randomness to it, which is called an IV, and we get a better security because essentially we try to not reuse them, and then even if you know the IV, you're gonna have a very hard, because you cannot run the cipher randomly again with that same IV, then you're gonna have a very hard time like taking back what was done. Yes?
I guess another point of clarification is that the stream cipher is just a scheme for generating things that are like one-time paths.
Exactly. Yeah, exactly. You're simulating a one-time path.
Initialization vector, if you never use the same one, you're basically compressing your one-time pad into the space that's represented by the
Exactly. So your initialization vector would be kind of mapping your stream into a different space, into a different distribution. And that's the nice part about it. And now we're gonna go back to block ciphers. And we're going back, but this is the first time we've actually talked about it. That block ciphers also need modes of operation because they cannot handle inputs with arbitrary lengths. And any length of a block cipher usually has to be a multiple of the block size, because otherwise you can't. It operates on blocks, on fixed length blocks, no more, no less. So essentially, we have the most common modes, and every other mode that's out there right now, most of them are built upon these primitives. The first one sucks. Never use it. It's called ECV. It's not doing anything. It's literally just running your cipher block on every single input and output. And it happens that that actually does not hide information very well. I will show you guys the ubiquitous picture of ECV mode, which is the Linux penguin. And encrypted with ECB mode, it looks like that. You can literally see the penguin, right? Because if you think about it, like if you're thinking about this image in bits, it's mapping the black bits to the same black bits every single time. And it's mapping the white bits into the same little diagonal, I'm not sure if you can see it, but it's a little diagonal pattern every single time. So you're not actually hiding a lot of information that way, which, sucks. So you don't want to use ECB. F5. Now CBC is one that has been secure, but is not the best and most recommended right now. CBC is essentially this scheme, and I'm going to write it on the board because that's a little bit hard to see. Because I really suck at LaTeX and I cannot center my images. So that's exactly. So if you see even the images that fit pretty well, you're going to see them a little bit tilted to the side because I don't know how to center them. So but it's okay. I got my awesome marker skills here for that. And by the way, you know what? It's been 40 minutes. This is what I'm saying. Like even with 6 hours, I don't even have enough time, which is awesome. Because cryptography is awesome. Anyway, so we're gonna start off. We have our IV, which is our nonce. We generate this randomly. Again, we have more randomness. Might be a little bit confusing, but the IV is also it can be generated randomly. But in CBC mode, usually we do care about it being random. So we have our IV, and then we have our message, right? And our message, we need to essentially do stuff on it if it's not the exact length of the blocks, if it's not a multiple of the blocks. So like little, very simple mathematics. If a message has like length, actually, wait, I'm not writing LaTeX. So there's a really nice L that I don't know how to do. But anyway, if a message has length L, I don't know how to write that there. But but if a message has length L, you need that L to be essentially if you have block length n, you need this to be an integer, of course. It needs to be divisible. Otherwise, it's not going to be able to operate on the fixed length blocks. So worst case scenario, if it's not, you have to pad it. And there's different padding schemes. And now that you guys probably understand it more, this is exactly where padding oracle came in. But before I go in there, I'm going to talk about what it actually is. And it's a really simple construction. So first you take your message with your IV, and then you XOR them together. That is your initial randomness that you're adding.
This would be some first fixed length piece of your message.
Yeah, exactly. So this is any block that I show here is of length n. So length is equal to n. Yes.
I'm sorry, I totally missed what IV is.
Nonce, just random number.
Okay.
IV, it's just called IV because the actual representation is a bunch of bytes. That's it. Great. It can be, usually, for example, for AES is 128 bits, or 256 bits, or 192 bits. But it depends. Depends on the mode as well. But you take your IV, you XOR it with a message, and then you feed that into your encryption. We're talking about encryption now, ENC. And we're going to say ENC sub k because we already initialized this with some encryption function, right? And now here we get. So remember, we're gonna call our message m, and then we're gonna call the divided blocks. We're gonna call them m1 to ml over n, of course, for l being the length of the message. So we take that and we have our C1, right? This is pretty simple. This is nothing has happened. Now we take the actual output of that C1 as well. Beep. And then we run the same thing that the IV did at the beginning. Now we're actually XORing with the output. And same little black box, C2, and this continues onwards. What happens is that makes your encryption of a particular message. A singular bit change is going to change the encryption, the whole rest of the message. And that's the whole point of ECB mode, CBC mode. And that's why, that's where the security, the appeal came from. The encryption is also similarly easy. I forgot the diagram, but it's pretty much like you take your, by the way, encryption for CBC mode has to be done in sequence because every single ciphertext depends on the plaintext, right? This is just a property of it. There's no way of getting around it. Yes?
The difference is the ECB is kind of like in parallel, whereas CBC depends on the initial guy.
Yeah, but we don't care about ECB's parallel because it sucks.
No,
it doesn't hide anything.
I understand the difference between the two.
Oh yes,
So
sure.
that's parallel, and this one uses the previous guy as
Exactly. Yeah, that adds more randomness. Because also, the thing about these pseudo-random functions, right, is that a singular change is supposed to map to a completely different distribution, right? So in practice, that even happens in the AES. You change a single bit, and your output looks completely different, and that's what you want. And then decryption looks very similar. You take your ciphertext, and you have to know your previous blocks, of course. You have to know your C1 and your C2. Then this goes into the decryption function, DC sub k.
And why are we breaking up the message into
blocks?
indexes?
Because it only operates on fixed lengths.
Size length.
Exactly. So you got to divide it up. Then you take essentially the next ciphertext and then you XOR to get the plaintext. P1. And then this one can actually be done in parallel. Yeah.
I just wanted to kind of help motivate the use of blocks.
Being really helpful. Great.
With stream ciphers, it's purely substitution. One of the other things that we can do to scale messages is something called transposition, where not only do we substitute one for another, but we also mix up the positions.
Okay.
However, if you ever tried to reverse an infinite list, right, you can't do it. And so we introduce these finite set of blocks so that we have some sort of finite space over which we can transpose the things.
So you're actually talking about implementation, and stuff like that is actually, for example, how AES works. So I'm talking about mixed column, what's it called? S-box substitution boxes. I'm not getting into that because it's almost been an hour, and I could spend another hour on AES. But you're right, and this is useful information. But I'm trying to avoid very specifics because of that, because I can spend a lot of time on them. And I speak fast, so it's a lot of stuff. Yes?
All right, so the initial vector is not key, it's just an extra bit.
No, exactly, yes. Exactly.
Is it needed for decryption?
Yes, of course, because you added some randomness. So imagine you're adding some randomness, and then you're changing essentially the output of the function. Because so imagine if without the IV, it's always going to map to a particular thing. When you add a random IV, it just maps to a different thing, right?
Where would the IV go in this diagram?
Well, I mean, in the decryption one, just right at the end. We're literally just reversing these arrows, right? Because the decryption function just runs backwards. So it's going to go all the way until the last ciphertext, right? And then once the last ciphertext, does its thing, run it through the little box, we're going to have to XOR this one with the IV. We're just running the arrows backwards. It's the same thing. Like if I were to flip that diagram upside down, that's exactly how decryption works. But because of that, because you already know in decryption every single ciphertext block, then you can run it in parallel. And CTR mode, CBC mode, is not exactly very praised for its parallelism because you kind of want it in both. And if we revisit the padding oracle attack, which is a super simple thing, what happened? So there's something called PKCS 7. And PKCS 7 is exactly how you format your blocks. So I'm going to talk about the simplest block I can think about is, let's say we have a block cipher of length 4. This is exactly why it serves us to speak about these abstractly, because I can just change lengths randomly and it works. So we have a block cipher of only 4 blocks, of only 4 bits. It operates on only 4 bits. And on this block cipher, we have a message that's only 2 bits. It's just maybe OK, right? It's 2 bits. So on this message, let's say OK is 10. We have to do something to it. Now, PKCS 7 is a very simple one. The number of bits that you're missing, number of bytes, actually. So PKCS 7 operates on a byte level. And I'm sorry if it's a little bit confusing, but usually when we're talking about block length, we talk about it in bytes, not bits, because block length is, for example, it's like 128 bits or 16 bytes. But PKCS 7 works on a byte level. So actually, let's change this to bytes. So this is 0x1, 0x2, right? Or something like that. PKCS 7 is simply just however bytes you're missing, you just put that in there in the rest. So this one we're missing 2 bytes. So every single one is just going to be 0x2, 0x2. That's it. If we're only transmitting a single byte, we erase this one, and these are all going to be 3. Right? So you can think about how a software developer might make an error and to throw an error if it doesn't conform to that specific thing, right? Because if you know ahead of time that you're using PKCS 7, you know that if it doesn't end in 030303 or 020202, it's an error, right? You know this. This is like always going to happen. And then you leak information, and that's exactly how these padding oracle attacks happened. And it's a very simple concept, but it's very powerful, and it builds up on everything that we talked about. And it's literally just a minor thing. Just, some developer wrote, if this thing doesn't conform to this shape, throw exception. And it happened to be a vulnerability. So now let's move into counter mode. And counter mode is a really, really, really simple construction, but it's really, really good with a caveat. Counter mode is actually turning a block cipher into a stream cipher. So we're not talking, no padding. Why? Because now we have our nonce, our IV or nonce. I'm going to start writing IV/nonce because I think it's confusing people. But we have our IV or nonce, right? Every single one has to have an IV or nonce. And remember that IVs and any sort of fixed length bits is essentially a number, right? We can consider it a number. So let's call this, let's say this is 0001, right? What we actually do is that we run only the IV through the encryption function. So this is our ENC sub k. And then we get, of course, some fixed length block, right? Some length n. Then we just take our message, let's say our M1, and then we XOR it right here. Oh, sorry. I'm bad at diagrams. We XOR it right here. Sorry about that. We XOR it right here, and then here we get C1. We made it way at the bottom. But, and then we just continue onwards, because this is a counter, so we just increase over the next one. And it's a super simple concept. If this is 001, this part is now 0002. And I mean, in practice, these are, 128 bits, so it's not just, 4 bits. So it's, of course, it's a lot more secure. Yes?
What's the second box say underneath IV nonce?
Encryption K. ENC sub K.
Okay.
And then this thing, just imagine mirroring this, except for instead of M1, now this is M2, and this instead of C1, this is C2. And that's it. It's parallelizable, it's simple, it's easy. And it's the simplest thing, but now we're going to break it.
The performance benefit you get into it is you can skip into a middle part of the
Yeah, of course. And actually, there's a tax because of that.
Really?
Yeah, there are. And I was going to mention essentially CryptoPals. CryptoPals is a set of really interesting cryptography exercises that are language agnostic. This specific exercise that we're going to touch now on the repo is using CryptoPals, is essentially an idea from CryptoPals, but of course just a simple understanding of this. But we're going to talk about what happens if this thing is not actually random. Right? What happens if we encrypt a bunch of messages with the same thing? Now, for whoever doesn't have the repo, it's this LC crypto exercises. So I'll give you guys a few minutes to fork, yes?